Hello viewers, I am Dr. Mala Das Sharma, retired professor of St. Pius X Degree and PG College for Women, Hyderabad. Welcome to my channel Chemphilic. Let's start 26th episode of Teaching Chemistry through Riddle. Do watch the video till the end and enjoy the complete riddle. So let's start riddle number 26. You can prepare X in variable composition by adding liquid A to B or B to A in different proportion. Preparation of X from A and B is accompanied by absorption of heat. X bears a lowest boiling point lower than even the boiling point of both A and B at a particular composition. If you apply fractional distillation process to X, you can get back only A as residual liquid up to a certain range of composition of X, but distillate will not be B. For other range of composition, distillate will remain same, but residual liquid will be B. So this is our riddle number 26. Now let's see the questions. The first question is, what is X? Second question, name the particular composition of X which has lowest boiling point. Third question, what can be obtained as distillate during fractional distillation of X? Fourth question, what are the reasons for the heat absorption during the preparation of X from A and B? Now let's solve the riddle and get the answers of all the questions. See, the riddle, the first clue is given. You can prepare X in variable composition by adding liquid A to B or B to A in different proportion. That means X is prepared by mixing the two liquid. So it is a two liquid mixture. So two liquids mixture, it may be completely miscible liquid-liquid homogeneous mixture, or it may be partially miscible liquid mixture, or it may be the completely immiscible. But in the later part of the riddle, we observe that fractional distillation can be applied. So X belongs to the category of completely miscible liquid-liquid solution. So this completely miscible liquid-liquid solution is of two types. Ideal solution and non-ideal solution. Non-ideal solution, once again, it is of two types. Non-ideal solution showing positive deviation from Raoult's law. The second one showing negative deviation from Raoult's law. Now, first let's see what is Raoult's law. Now we know that if you take a liquid, if it is volatile liquid, then some of the liquid is converted to vapor and this vapor present above the surface of the liquid and this vapor exert a pressure on the surface of the liquid. That pressure we call it as vapor pressure at a particular temperature. Now it is a mixture. Completely miscible liquid-liquid solution. Two components are there. Both are volatile. From both the components, vapors will be formed and the vapors of each component will exert a pressure on the surface of the liquid. In that case, that pressure exerted by the vapor of any component on the surface of the liquid is known as the partial vapor pressure of that component. Now, Raoult's law states that partial vapor pressure of each component in the solution at a given temperature is equal to the mole fraction of the component in the solution. Mole fraction means number of moles of that component divided by total number of moles of all the components present in the solution multiplied by the vapor pressure of that component in the pure state at the same temperature. That means the vapor pressure of the component when you are taking it in the pure state at the same temperature. So, according to Raoult's law, partial vapor pressure of any component, say component A or solvent component, must be equal to chi A, that is the mole fraction of A in the solution, multiplied by the vapor pressure of A when it is taken in the pure state at the same temperature of the solution. Similarly, the partial vapor pressure of B also can be represented by this Raoult's law equation, chi B into P0B. Now, the characteristics of ideal and non-ideal solutions. The first one, molecular interaction. Now, when you are preparing the solution, then solute molecule is entering between these solvent molecules. Initially, there will be some intermolecular attraction or molecular interaction present between the solvent molecules. Now, when the solute molecule enters, then between the solvent and solute molecules, intermolecular force of attraction developed. Now, in case of ideal solution, this solvent-solvent intermolecular force of attraction is identical to that of solute-solute intermolecular force of attraction, and that is identical to that of solvent-solute intermolecular force of attraction, which is developed when the solution is prepared. Now, for non-ideal solution showing positive deviation from the Raoult's law, in that case, when the solution is prepared, this intermolecular force of attraction between the solvent and solute is weaker intermolecular force of attraction developed than that of the intermolecular force of attraction between the solvent molecules or between the solute molecules. Now, in case of non-ideal solution showing negative deviation from Raoult's law, just opposite things happen. That means intermolecular force of attraction developed between the solute and solvent molecule will be stronger than that of intermolecular force of attraction which was present between the solvent molecules or between the solute molecules. Now, second point is enthalpy of mixing. Enthalpy is thermodynamic term. It is the total heat content of the system. Now, during this mixing, how much is the enthalpy change? So, its enthalpy remains constant. Why it is 0? Because when you are adding this solute to solvent, then what happens? Between the solvent molecules, you have to break the intermolecular force of attraction, because in between the solvent molecule, the solute molecule is entering. So, you have to break, this intermolecular force of attraction between two solvent molecules, and for that energy is required. And similarly, when this intermolecular force of attraction develops between the solute and solvent molecule, then some energy is released. In case of ideal solution, energy required to break this intermolecular force of attraction between the two solvent molecule or solute molecule exactly identical to that of the intermolecular, to that of the energy released during the formation of this intermolecular force of attraction between solute and solvent. So, net result is no change in the energy. That means no heat is absorbed or no heat is released. For non-ideal solution showing positive deviation from Raoult's law, in that case what happened? More energy is required to break this intermolecular force of attraction between the solvent molecules or solute molecules, because this interaction is stronger than solute-solvent interaction, already I told. But when this solute-solvent interaction is developing, then less energy is released because it is weaker interaction. So, net result is you have to supply more energy. Okay. In that case, total heat content of the system increases. That means enthalpy increases. Therefore, delta H mixing is positive or greater than 0. Now, for non-ideal solution showing negative deviation from the Raoult's law, in that case, this solvent-solvent interaction or solute-solute interaction or intermolecular force of attraction is weaker. So, less energy is required to break this. But more energy is released when this solute-solvent intermolecular force of attraction is developed. As more energy is released, so net result is that heat energy is released. That means it will be exothermic process. In the first case, that is non-ideal solution showing positive deviation, energy is absorbed. So it is endothermic process, and it is the clue of your riddle. That means your X is non-ideal solution showing positive deviation from Raoult's law, because in the riddle it is given that this process is accompanied by absorption of heat. Now, next one, delta V mixing. Is there any volume change during mixing? For ideal solution, there is no volume change, right? Because once again the same, everything you have to explain from the introduction, because of this same intermolecular force of attraction between solvent-solvent molecules and solute-solvent molecules. So, the solute molecules will be in the same place of the solvent molecules after replacing it. So, there is no change of the volume. Now, non-ideal solution showing positive deviation from Raoult's law. For such type of non-ideal solution, as weaker interaction developed between the solvent and solute, because of the weaker force of attraction, these two molecules will be little far away from each other. As they are far from each other, then what will happen? Overall volume will increase. So, delta V mixing will be greater than 0 or positive. Now, for non-ideal solution showing negative deviation, here stronger interaction is developing between solvent and solute. So, because of the stronger attraction, they come close to each other, solute and solvent. So, overall there is a decrease in volume. So, there is a decrease in volume. The volume change is negative. Now, coming to the delta S, entropy of mixing. Entropy is the measure of disorderness or randomness. Now, for any kind of solution, ideal solution or non-ideal solution, when you are mixing the solute and solvent, number of molecules increasing, so disorderness increasing. Moreover, initially, if it is a pure solvent, only solvent molecules were there. That means it is an ordered arrangement. Now, when you are adding the solute molecules, if the solute molecules are coming in between solvent, that become disordered arrangement. So, disorderness increases. So, entropy change will be positive for ideal and non-ideal solution. Similarly, change of free energy, that will be negative, and for any spontaneous process, free energy change is negative. So, this preparation of the solution just by mixing the two liquids, it is a spontaneous process. You need not apply any external aid from outside. So, free energy change will be negative. Now, Raoult's law, this ideal solution obeys Raoult's law at all concentration and temperature. That means the observed vapor pressure of this solution will be same as that of calculated by using this Raoult's law equation. That means the partial vapor pressure of A calculated by Raoult's law equation plus partial vapor pressure of B. Now, a non-ideal solution showing positive deviation from Raoult's law, in that case, this partial vapor pressure itself will be greater than theoretical vapor pressure. Theoretical means calculated from Raoult's law of each component. So, observed vapor pressure of this solution will be greater than that of theoretical vapor pressure. That means vapor pressure calculated from this Raoult's law equation. Now, non-ideal solution showing negative deviation from Raoult's law. In this case also, this partial vapor pressure of the component will be actually less than that of calculated by using Raoult's law. That means less than theoretical value. So, the total vapor pressure of the solution also will be, or observed vapor pressure of the solution also will be less than that of calculated by using Raoult's law equation. Now, vapor pressure versus composition curve. Now, for ideal solution, look at here. In this extreme left, it is completely A. That means mole fraction of A is 1. Extreme right, it is completely B. In this direction, mole fraction of B is increasing. So this line indicates the partial vapor pressure of B, which is same as that of if you plot by calculating by using the Raoults law. Similarly, this is the partial vapor pressure curve of A. The observed value if you plot or calculated value if you plot, you will get the same curve. And this is the vapor pressure of this solution. Now, for non-ideal solution showing positive deviation from Raoults law, if you plot the calculated value of vapor pressure of B, then you will get this line, dotted line. But actually, observed value will be more than this one. Same thing is true for the partial vapor pressure of A. Now, for the solution also, if you calculate by using this Raoults law equation, this curve will be this dotted line, but actual vapor pressure will be more than that. Now, for non-ideal solution showing negative deviation from Raoults law, here also same thing. This is if you calculate the partial vapor pressure of B using Raoults law, then you will get this curve by this plot, but actual vapor pressure will be slightly down that of this one. Similarly, here also for vapor pressure of B also you will get slightly down, and total vapor pressure of the solution also less than that of the calculated from Raoults law. Now, examples for ideal solution, this both the components should have nearly same molecular mass, size and polarity. For example, NHN plus N-heptane. Now, for non-ideal solution showing positive deviation from Raoults law, water and ethanol. Here, initially, intermolecular hydrogen bonding is present between water molecule. Similarly, it is present in ethanol molecule. But when you are mixing, intermolecular hydrogen bonding is present between water and ethanol molecule, which is weaker than that of the intermolecular hydrogen bonding present in water molecule. Now, non-ideal solution showing negative deviation from Raoults law. Here water and nitric acid. Example. Now, ideal solution by fractional distillation, you can separate the two components for any composition of the solution. Let's see. Suppose this is the ideal solution curve. This side boiling point, this side composition. B is increasing this direction. Now, this lower curve indicate the liquid composition, upper curve indicate the vapor composition. Now, if you take any composition Y and if you start heating, it will start boiling at temperature Ty, and this is the composition of the liquid, and the composition of the vapor means you have to extend up to the vapor curve, and this vapor, if you condense, you will get the distillate Y1, and the distillate will be close to B, means rich in B, and obviously the residual liquid will be close to A or rich in A. That means if you repeat this fractional distillation, finally you will get pure liquid B as distillate and pure liquid A as residue. For any composition of the solution, you can separate A and B by fractional distillation. Now, for non-ideal solution, any one component depending on the composition of the solution can be separated by fractional distillation. Now see. So here also same boiling point versus composition. Now here you see there is a solution of a particular composition which I have denoted here by C, which has the minimum boiling point. Minimum in the sense its boiling point is less than the any other composition solution, and it is less than that of the boiling point of pure liquid A or pure liquid B. Now, if you take any composition between A and C, say I have taken X, and if you heat it, it will start boiling here. Then composition of the vapor means this one. If you have to extend the line, then if you condense it, the distillate will be X1, which will be close to C. That means rich in this particular composition liquid, which we call it as azeotropic mixture. And here it is azeotropic mixture of minimum boiling point. And the residual liquid will be close to A. So if you repeat the fractional distillation, finally you can separate the pure liquid A as residue and the azeotropic mixture C as distillate. Similarly, if you take any composition between B and C, then by fractional distillation, C distillate will be Y1, that means close to C. That means if you repeat it, you can separate C as distillate and the B as pure liquid. But AB at a time you cannot separate. Now, azeotropic mixture, it looks like pure compound because it starts boiling at a particular temperature and the temperature remains constant, still all the liquid boils off, but it is not the pure liquid. This is due to the fact that the boiling point and the composition of the azeotrope changes with pressure. But for chemical compound, pure compound, this boiling point and composition remains constant over a range of temperature and pressure. And here it is azeotropic mixture of minimum boiling point. If you take the non-ideal solution showing negative deviation from Raoult's law, then you will get azeotropic mixture of maximum boiling point. Now coming to the answers of the other question. Question number 1, what is X? Now you know, non-ideal solution showing positive deviation from Raoult's law. Question number 2, name the particular composition of X which has lowest boiling point. This is azeotropic mixture of minimum boiling point. Number 3, what can be obtained as distillate during fractional distillation of X? And it is azeotropic mixture as distillate. And then fourth question, what is the reason for heat absorption during the preparation of X from A and B? Because as weaker interaction develop between solute and solvent, and solute-solute interaction and solvent-solvent interaction is stronger, which has to be broken. So heat is absorbed during the formation of such solution. So this is the end of the riddle number 26. Thank you.